Hey, John here from Science Tips. Today I bring you a lesson on atomic models. This is grade 10 chemistry. Thank you very much, and I hope you're going to learn together. Let's get into it. Uh, we're going to learn about atomic models. These are all about how we understand the atom as of today and how that has evolved with time. So we are going to first of all define what atomic models are and discuss the importance. We're also going to list all the atomic models that have been developed and describe them. And finally, we'll also look at the weaknesses and strengths of each atomic model. So first of all, what is a model? The description or the definition found in the dictionary is that it is a simplified description of a system or process to assist in calculations and predictions. So this is the one that mostly suits this topic. And what we can get from this is that it is a simple representation of a complex system. So think of some engineers trying to design a complicated plane or ship or a building. They have to first of all come up with a smaller miniature replica of what they want to create, and first of all study it, and then be able to transfer those what they have studied into the original, or maybe more change the model so that at least they be able to understand. For our case, it helps us very much because we cannot be able to observe the real atoms because of their small size, and we are able just to look at their behavior and be able to at least make a model of how they look like and how they behave. So the model helps us visually understand the real object, how the real objects may look like and how the real system may behave. So having said that, this is a list of all the atomic models that have been developed over time. And first of all comes the Dalton's atomic model, named after its developer. It was developed in 1903. Then it lasted for a whole century up to 1904. That's when Thomson Plum pudding model was put forward after the discovery of electrons. Then Rutherford's nuclear model came in 7 years later. As you can see, it's called nuclear model. This is when now the nucleus was discovered. And then later on, after 2 years, uh, another model replaced Rutherford's model, trying to improve on it, called Bohr's atomic model, which also served for an impressive 13 years before the current quantum mechanical model was developed in 1926 by separate scientists who provided separate information, which was put together to get quantum mechanical model. Among the top developers of this, or who contributors, are Erwin Schrodinger and Heisenberg. Please tell me from which countries they come from, because they uh, provided very impressive science to it. So let's start with the first one, Dalton's model. First of all, Dalton postulated that atoms are indivisible. So they were the smallest, at the time, they were the smallest particles that make up matter. And he also said that atoms of the same element are identical. This is also very important, although it came to change, but by then, it was a very huge observation. He also said that atoms can neither be created nor destroyed. So this provided some conservation of mass, even in reactions. And he acknowledged, yes, that atoms combine with other atoms, but they do so in whole proportions, whole ratio proportions, forming compounds. So there was no concept of subdividing. So this is the visual representation of Dalton's atomic model. The atom was just a sphere, which was the smallest known part of matter, and it could not be divided, and it could also react by combining with other atoms of either different elements, but doing so in whole number ratio. This model served us well. One of its best strengths is that it was the very first model in an attempt to understand the atoms. Secondly, it was also able to show that matter is conserved, or mass is conserved. All matter is only transformed from one form to another, but atoms could not be created nor destroyed by then. So some of the sharp weaknesses or critics of Dalton's atomic model have put forward is that the model was not able to show that there are smaller particles than the atom. So it was later replaced after about 100 years of serving scientists well by a better model called Thomson's model. And as we said, remember we said this is Thomson's plum pudding model. And this is after, during experiments, J.J. Thomson was able to discover that there are negatively charged particles inside the atom. And he put forward a model that says that the atom is a positively charged sphere, and then we have negatively charged electrons embedded within the sphere, just like raisins would be embedded in pudding. That's why it's called Thomson's plum pudding model. He also said that atoms are divisible. So, of course, this comes from that now the electrons are distinct. And then it recognized that electrons are distinct subatomic particles that we have already said. And at that time, one of the weaknesses is that protons and the nucleus were not yet discovered. So after some good years of service with Thomson's model, it was replaced by Rutherford's model. But here is a picture representing the Thomson's plum pudding model. So these here, the small particles inside the sphere represent the electrons, which are negatively charged, while the sphere itself was positively charged. So just as to match the positive and negative. But this model was not able to describe or to show the stability of atoms. So Rutherford's model came next. And one of the propositions of Rutherford was that most of the atom is empty, and there is a tiny, dense, positively charged nucleus found at the center of the atom. And why is this so? Rutherford had carried an experiment where he bombarded alpha particles on a gold foil, and most of the particles, because they were positive, they went through, they were not deflected. Very few are deflected to different angles, and then some of the alpha particles were sharply deflected back to the source. And this could only mean that at the center there was a very dense positive nucleus. So because we know positive and positive repel, yeah. So and so he said that most of the atom is empty. That is where all the matter, all the alpha particles passed and deflected. At the center is the nucleus that is positive and dense. It had a lot of mass because of the sharp deflection. And then electrons are moving around the nucleus. So these are solved. The strength of this model is that it is solved the experiment, the gold foil experiment controversy, and it was able to explain. It was also able to show that there is a nucleus. That's why Rutherford's model is also called Rutherford's nuclear model. So here is an illustration of Rutherford's model. The electrons are moving around the nucleus, which is at the center. Now, after this model, there was need for improving it, and Bohr came with a new model. The problem was that when electrons move around the nucleus, the classical laws that were there at that time predicted that electrons would follow a spiral path and would be drowned in the nucleus. Now that the electrons are negative, remember they are also attracted by the positive nucleus. So why was that not happening? So Bohr came with the next model, and he said, and number one, that electrons move in fixed circular paths, which he called energy levels. That was just a postulate. He just put that forward. And then also proposed that electrons do not lose energy while in the permitted paths. So this would only mean that they would maintain their energy, and that would prevent them from spiraling towards the nucleus. And the only time electrons lose energy, they only emit or even absorb energy, is when they jump from one level to another. So the model explained the spectral lines for hydrogen and small hydrogen-like atoms, but it failed to describe spectral lines for complex, the peaks and dips for complex atoms with many electrons and all that. So this is a model of Bohr atomic. This is Bohr atomic model. You can see the mass at the center, and then the electrons are moving around the nucleus, and specific number of electrons in each orbit. So after Bohr's model, there was need also to improve on it and explain further the spectral lines that were produced by complex atoms like this one, oxygen. So the one that replaced the Bohr model was called quantum mechanical model. Other books will call it the Schrodinger-Heisenberg model, and it was developed on the principles studied by different scientists like Erwin Schrödinger and Heisenberg. Once again, tell us please where they came from, which countries they came from, because they contributed enormously towards science. So quantum model, one of the postulates says that electrons have dual nature. Dual nature, that means that they behave both as particles and waves. That would explain best why they were not spiraling, because I will have to explain or to give the we would be able to give the practicality of why they would be moving around the nucleus without spiraling, and again emitting very discrete amounts of energy. Discrete meaning very much quantized, and every electron would emit a certain specific amount of energy. Another postulate on which this model hangs is that the position and momentum of electrons cannot be determined at the same time. so simultaneously. This is called a Heisenberg uncertainty principle, and it helps. It is one of the weaknesses of the model, but it was a painful revelation that probably you'll have to live with it. And these changed the way we understand the atom drastically, because now the fixed paths proposed earlier by Bohr could not hold. And now electrons would be found not in very specific places or specific paths, but in probabilistic regions called orbitals. Uh, the model was successful in explaining spectral lines for all atoms, although it comes with a lot of pain in deriving mathematical equations. I think those who have studied quantum mechanics can attest to that. So anyway, but this is not to scare you, but honestly, Aaron Schrodinger did a very good job, uh, but has tortured many students anyway. So this is the quantum mechanical model uh, for oxygen atom. These are some of the orbitals that are developed. For the first energy level, there is only one orbital. A type of orbital called S is a spherical orbital. Then we have the same kind of orbital, but at a higher energy, belongs to energy level 2, and 3 orbitals called p orbitals. And each orbital has space enough for only 2 electrons with opposite spins. All these are governed by a set of solutions to the Schrodinger equation that they are called quantum numbers. But basically, these are some of the orbitals that were developed. Anyway, some of the things might be a little difficult for now, but with time, you'll be able to get them. So, wish you happy learning. Please subscribe and keep tuned for more lessons. Thank you.